All right, what we're going to look at now are a couple of example problems that use some of these similarity theorems in order to find missing measurements or to verify that we're looking at similar figures. So a common example you'll see is one that uses a triangle with a parallel line in it. So there's a line right there. Actually, let's not even say it's parallel. Let's just say the line's there. And we'll put some measurements on here. So maybe we'll put a 2 and a 4 and a 3 and a 6 there. So we've got that as our figure. Now the question is, are the two triangles similar? And if they are, let's just leave it at that. Are the triangles similar from what's given? Now remember, we've just talked about 3 different shortcuts to prove two triangles are similar, meaning they're dilations of each other off of some dilation point and possibly rotated. Now this example shows, actually, if you look, you can see a dilation point, and you can see how the smaller triangle here has been dilated into this larger triangle here. So there are the two triangles we're going to compare. Now, we have a couple of rules that we're going to kick in order to say for sure that these are going to be similar figures. What I'm going to use for this is the side angle side similarity. I'm going to show that I have two proportional sides, pairs of sides, and then a congruent angle. Now, angle C is repeated. That means that angle C will be congruent to itself. Now, the property that tells us this is true is called the reflexive property. Now, reflexive means something equals or is congruent to itself. That's an actual name for the rule, even though you think it's pretty obvious. I mean, if I tell you angle C is 60 degrees, how big is angle C? 60 degrees. So that's not too bad. Now I want to show that the yellow triangle sides are going to be proportional to the pink triangle sides. So what I'm going to do is I'm going to take 2 divided by 6 and see what I get. Now, why did I divide it by 6? The pen's being a little silly here. 2 divided by 6. Why 6? Well, the reason I'm using 6 is this side of the pink triangle is 6 units. Just like this side of the pink triangle is 9 units. So the other fraction I'm going to have to check is 3 over 9. Now, the good news with this is that as long as I'm working with just the smaller parts, the proportions still work out. See, there's a little wiggle room. You can get it wrong, but still get it right. The problem is when I go to compare these sides here to see what happens, because again, they're going to use this larger scale factor. 2 over 6 is 1/3. 3 over 9 is 1/3. Since my pairs of sides are proportional, so I have 2 pairs of sides proportional, 2 pair proportional, and I have a congruent angle, I can conclude that the triangles must be, so triangle ACE must be similar to triangle BCD. Again, and that's by SAS, similarity. I've shown some sides are proportional. That means I have a common scale factor for them. And I've shown that there's a common angle. Both the triangles, the yellow one and the pink one, share the angle C. So that would be my third condition. That means I now know these triangles are going to have to be similar, and I can make other conclusions from that. So let's move now to a problem that's going to use both proving things are similar and going a step further and finding a missing measurement. I'm going to work with a similar diagram. So again, I'm going to work with this triangle here. Oops, let's do it all in one shot so it stays linked as a single triangle. There we go. And I'm going to add a line on here. So there's that extra line. Let's move everybody over a little bit so we have some room to work. There's that. Now in this case, I'm going to give to you that these sides, oops, no, we'll take it, are parallel to each other. Now from what we've talked about in previous units, that tells me quite a bit already about the picture I'm looking at. Let's say this over here is going to be 10. And we'll say this over here is going to be 6. And let's say this here is, looks like maybe we'll call it 5. And I want to know, well, let's not do 5. Let's do 4. Let's do 4. I want to know what that is. Now, some things we've talked about. That would be the problem I'm handed. First, are these similar? Second, what's x got to be? Now, I don't have any angles marked off, but I have that parallel. That makes me think of a couple of things. For example, this angle right here and this angle right here are corresponding angles. I can see two parallel lines cut by a transversal. So that means I'm looking at corresponding angles. Likewise, these angles are going to be corresponding angles. Again, my red lines are my parallel lines. In this case, my blue line is my transversal. So that means these triangles must be similar by angle similarity. I have two pairs of angles congruent between the two triangles. And now again, remember, I'm working with these overlapping triangles. I have this green triangle here, and I have this orange triangle here. So my two triangles are overlapping. Now I can do a proportion. I'm going to take a measurement off the big triangle and match it to a measurement off the small triangle. So I can write 10 is to 6 as big triangle x is to 4. That proportion will look better if I use my math tool. 10 is to 6 as x is to 4. That proportion comes from the fact that I've said these two triangles are similar. So triangles are similar because two pairs of angles are congruent. Now I can solve my proportion. Cross multiply gives me 40 equals 6x. I'm going to get a decimal answer now. So 40 divided by 6 puts me at x is equal to 6.7. And that's that whole side there where x is marked off. A lot of what makes this unit work is remembering the rules about parallel lines that we learned in Unit 2. So things like corresponding angles, alternate interior angles, and watch for vertical angles, because they'll oftentimes also take us another step and show us angles that match up that let us use one of the 3 triangle similarity theorems that we've talked about. Let's tackle one more example before we call this good. Third time's the charm, right? In our third example, I'm going to work again with those parallel lines. So here's a line, here's a line. We're going to say they're parallel. I'm going to cut them by a couple of transversals. Now, if those two lines are indeed parallel, it does follow that we're going to get all kinds of angles congruent. So now I can start to set things up. I'm going to call this measurement here. Let's call that measurement, let's call it 3. We'll call this measurement over here 18. We'll call this measurement x. We'll call this measurement 2. Now this is a good example of being able to look at a problem and probably suss out the answer without having to set the proportion all the way up. But remember, you want to avoid too many shortcuts during the learning phase. You really want to make sure you don't develop bad habits. Now, I might ask, do I know these lines are going to be parallel? Well, there's lots of things I can see happening. I'm sorry, these triangles are similar. Is triangle 1 similar to triangle 2? Well, some things I know coming in. One thing I know going in, for example, let me get that number out of the way, it's going to mess things up, is that vertical angles are congruent. I also know that alternate interior angles are congruent. So there I've got my two pairs of angles necessary to show that I have similar triangles. And again, I'm going to be using angle, angle, similarity. So I know these two triangles have to be similar. For practice, let's write down the similarity statement. A, B, C, D, and E. So that means if I were to write down my similarity statement, I would write that triangle A, B, E is similar to triangle D, B, C. That statement tells me what's going to be similar now. It's going to pair up the sides that are similar to each other and show me which vertices are going to have the same measures. You can see here, E and C are both the last letter. And it just so happens that E and C are congruent angles. That's part of what the similarity statement shows me. Now, taking that the next step, I can write my proportion. Let's see, I'm going to go 2 is to x as 3 is to 18. The other nice thing with this is you have a certain reality check that kicks in. When I cross multiply, I get 3x is equal to 2 times 18, which means 3x is equal to 36. Thus, x is equal to 12. And I can ask myself, does this answer make sense? On the one hand, I could say, well, 3 times 6 would give me 18. It looks like I have a scale factor of about 1 to 6. Use that philosophy then with the 2. Scale it up. 2 times 6 puts you at 12. You're also going to want to be comfortable talking about the scale factor for each of these diagrams. In this case, my scale factor of small to big, which is going to be 3 to 18, is a scale factor of 6. That's something else that we've been talking about that's going to keep coming up as we move through this content. All right, hopefully this got it started. When we come in next time, we're going to be looking at more of these particular problems and trying to show that certain pairs of triangles are going to be similar.